Before visiting specific regression techniques, let's take a look at regression problems as a whole. We've already looked at classification, which involves categorizing a case into one of a set of predetermined classes or categories. And regression, on the other hand, as we've already discussed, determines a specific number for an attribute. Okay, it usually predicts a number for an attribute. So classification is about taking a case and putting it into one of a few categories. And regression is about taking a case and predicting an attribute, a numeric attribute. Of course, as we've already discussed, predict in English, of course, is talking about the future, but predict in the context of predictive analytics may not always be about the future. We have seen some examples of this. So classification example would be given a credit card transaction, predict if it's fraudulent. But of course, this is not a prediction because the transaction has already occurred. And therefore, what you're really doing is trying to determine if this transaction which has already occurred was fraudulent or not. Okay, we call it loosely predict because we are just determining a value for something that we don't know. So in regression, we are talking about making numerical estimates of things whose values we do not know. So for example, how many units of a product are going to be sold, how many people might visit a kiosk, what is going to be the price of a particular stock, how many passengers may take a ride on a cruise ship on a particular route, how many people may attend a game, what might be the rainfall during a week or during a day or during a year. And in a restaurant context, it might be how much demand is going to be for a particular menu item. So all of these are things where we are determining an actual numerical value. And we use the term regression broadly when this kind of prediction is what we are doing. So before we get into actually building regression models, let's look at how we are going to measure the quality of a regression model. After all, we can build many regression models for a particular problem. And when it comes down to choosing which model we are actually going to use, obviously we would like to choose the model that has the highest quality. So we want to talk about how do we measure the quality of a regression model. In particular, we'll speak about a measure called the root mean squared error or RMS error. Okay, so this is common to all the techniques, and some other techniques, some techniques have their own specific ways of measuring quality in addition to the root mean squared error. So the quality of a model, of course, when it came to classification, we measured generally by looking at the error matrix and computing various numbers based on the error matrix. For example, what is the overall accuracy and what is the accuracy for a particular class and so on. And of course, we know that we came to the error matrix because a classification model would predict the probability of a particular case belonging to a particular class, and then we use a cutoff probability to determine the actual error matrix. So all of this we've looked at. So the question is, in regression, what are we going to use? Okay, so looking at a regression model, let's say this is our data set. We've got 5 attributes, and let's assume that attribute 5 is our target attribute. Of course, in this case, it's numeric because we are trying to, because it's a regression problem. And there are, of course, these 4 attributes that have values that I have not shown. Okay, so we've got our data set with the values of the target attribute. And let's say we've got a model for this. And of course, we'll be looking at specific models as we go forward. So right now we are talking generically. So we've built a regression model, and therefore, of course, the model is capable of making a prediction for the target attribute. We are going to look at the quality of the model simply as how close are the predictions to the actual values. Okay, really that's all we did for classification as well. And it's the same thing we're going to do with regression. Only thing is, with regression, we've got numerical predictors, and therefore the way in which we measure the quality of the model is going to be different than what we did with classification. So here is our target attribute, attribute 5. Here is one model that made a prediction, and here is the predictions made by another model. Okay, so you'll see that the attribute 5 values are of course the same because it's the same data set, but one model made these predictions, another model made these predictions. Okay, so it'll be a good idea for you to take a look at these two models and come to your own conclusion as to which model you prefer. Might be a good idea for you to stop the video at this point, take a look at the data carefully, and think which model would you prefer given these two models. Okay, so model 1 appears to be better. Why do we say that? We say that because the model 1's predictions in general seem to be closer to the real values than our model 2's predictions. Okay, we could have just done that by eyeballing it, right? If you just looked at each value and looked at the things, you would see that the differences here in model 2 are much higher. In other words, the predictions made by model 2 are in general further away from the actual values than are the predictions made by model 1. Okay, so in these two tables, I'm showing you the actual difference. And of course, you can see that the differences here are somewhat larger than the differences here. So in general, we would say, okay, model 1 is probably the better model of the two. How do you compute the root mean squared error? I had already pointed out to you that the measure of quality for a regression model is the root mean squared error. Okay. Now, of course, you may say, why don't you just add up the differences and take the one for which the total of the differences is smaller? For one thing, of course, the differences can be positive or negative, and therefore negative values might cancel out with some positive values. So that's not a great idea. But you could also say, well, instead of taking the absolute differences, why don't you take the absolute value of the differences? In other words, minus 19 will become 19, 12 will remain 12. In other words, convert all of them to positive and then add up the difference and take the model which gives you the lower difference. That's an approach, yes, that will actually work. It's not too much of a problem. But in statistics, they found that when you square the differences, in general, the squared value of the differences has many good properties. Okay, so that is the reason that people use the square of the difference rather than just the actual difference itself. Okay, so let's take a look at the root mean squared error, right? So you've got the differences, you square the differences, okay, instead of just taking the differences, and then you take the mean of that, and then take the square root of that. Okay, so that's what the root mean squared error is, right? So you first find the difference, square it, and take the average squared difference, and then take the square root of that. And that is what is called as the root mean squared error. In some sense, you can see that the root mean squared error represents on the average how far away from a real value the predicted value is going to be, right? Because this is the sum of mean of the squared errors. This is the square root of that, which is kind of representative of what the actual error is. Okay, so as I've said, the logic for this is somewhat mathematical, the logic for squaring, but in statistics you will find that this squaring of the differences comes up a lot. Okay, so that's the root mean squared error of the first model. This is the root mean squared error of the second model. And of course, as we already said, this first model appeared to be the better model, and our criterion for quality, the root mean squared error, bears this out. So the root mean squared error gives us an idea of, on the average, how far away from the actual value will be the predicted value. So that's what you get here. And of course, if you look at the units for the root mean squared error, the units for example, suppose these are number of, these are pounds, let's say, right? So the difference has units of pounds. The squared difference has units of pounds squared. And the mean of that also has units of pounds squared. But once you take the square root, the RMSE also has units of pounds. Okay, so it has the same units as the original quantity that you're measuring. And therefore, you can say that the RMS error gives you an idea of the average prediction error, or the average amount by which the predicted value is going to differ from the actual value. Okay, so let's just clarify how to compute the root mean squared error. Should be clear by now, but I just want to make it very explicit. Okay, so when you say root mean squared error, in reality, we are going to be calculating things in exactly the opposite order. So first you calculate the error, being the actual difference between the actual value and the predicted value. Then you square it for each row. Then you find the mean of it, of all the squared errors. And finally, you take the square root. Okay, so that's how you do root mean squared error. And in the whole regression module, we'll be using particular notation. So for example, the actual value of the target attribute for the ith row, we'll represent it as yi. So for example, y1 is the value of the target, actual value of the target attribute for the first row. y50 is going to be the actual value of the target attribute for the 50th row, and so on. Okay, and when we talk about the predicted values, we'll put a hat on top of the actual value notation, right? So y hat of I is the predicted value for y of I. Okay, so let's say the actual value was 100 and the predicted value was 114, right? So y hat is 114, y hat of I is 114, y of I is 100, right? So if we just go back to our previous table, for example, okay, so this is your actual, for example, yi, and these are your y hat i's, the model predictions. Okay, and therefore the formula for the root mean squared error looks like this, right? Because yi is the actual value minus y hat is the predicted value. We square that. So this is the difference or the error. We square it. And of course, we sum it up from I equals 1 to n, right? So when I is 1, you're doing the squared error for the first row. When I is 2, you're doing the squared error for the second row, and so on until n, which is the total number of rows. Okay, so the numerator here is the sum of squared errors. Okay, the sum of the squared errors, that's the numerator, divided by n, so that's the average of the squared errors, then square root is the RMS error. Okay, so root mean squared error, if you look at it this way, you're saying, okay, first you calculate the error, which is yi minus y hat I, and then you square it, which is the squaring of that, and then you take the mean, which involves, of course, adding it up and dividing by n, and finally taking the square root is this. Okay, so that's the overall way in which we compute the root mean squared error. Let's take a look at how to do all of this, the computation of the root mean squared error using R. Of course, it's very straightforward, nothing much to it. So here I've got a data frame that I'm just creating with some values. So I'm saying that is data.frame. So here, instead of reading the data from a file, I'm just creating a data frame on the fly. And I'm going to call the only column in this data frame as attribute 1, not only column, 2 columns. Attribute 1 is C 100, 200, 300, it's a vector of some values. And attribute 2 is some other values. And attribute 3 again has some values. Okay, so that's a data frame with 3 columns, attribute 1, attribute 2, attribute 3. And here is a vector containing the predictions that are made for this particular data set. Okay, so attribute 3 we are assuming is our target attribute, and preds contains the predictions that some model might have made for this particular target attribute. So for example, the first value of attribute 3 on the first row is 345, whereas the prediction said 300. The last value, actual value is 300, our prediction said 260, and so on. Okay, so how would you calculate the root mean squared error? Very simple, we are applying the formula. Here's the difference, that $attribute 3 minus preds. Okay, and remember this is vectorized, so it's going to do it for each value. This is a vector, that's a vector, so when you subtract 2 vectors, it's going to subtract every element and do the operation for each of them. So what this is going to do is to create a vector which contains the square of each of these differences. Mean takes the mean of that vector of the squared differences. Square root computes the square root of that mean, which step by step reflects our definition of root mean squared error. Here's another example. This time we put the predictions as a column in the same data frame. In the previous example, we had the predictions in a separate vector. This time the predictions are also inside the same data frame. Nothing materially changes. I just want to show you the different guises under which this RMS computation may occur. So in this case, obviously, instead of doing preds, you're going to say dat dollar pred because that's the column. Okay, so attribute 3, this is the actual value. Dollar pred is the predicted value. You're taking the difference, squaring them, finding the mean of the squares, etc., etc. Here's one more example. You've just got the two values in two different vectors. It's not inside a data frame of any kind. So dat1 is the vector of actual values, dat2 is the vector of predicted values, and we can compute the root mean squared error this way, right? So the two vectors are dat1 and dat2. Right? I just want to show you the different guises under which the computation of the RMSE might arise, right? So you may have the actual values in a data frame, predicted values in a vector, or you may have both the actual and predicted values inside a data frame. And in this example, you've got both the actual and the predicted values in vectors, separate vectors. But the basic computation doesn't really change at all. Now, another thing we could do is, since this computation is going to be done many times, we could write a function so that we don't have to write that complex expression again and again. So here I'm just showing you how you can create your own function to compute the root mean squared error. And incidentally, I'll also introduce to you how to write our function. So for example, I'm saying RMSE is a function. That's something new. You have not looked at it before. This is how you create a user-defined function in R, right? So you say function, and within parentheses, you indicate the arguments that the function is going to take. So in this case, the arguments are going to be two vectors, v1 and v2, right? One contains the actual values, the other contains the predicted values. It doesn't matter which contains what, because you're going to take the difference and square the difference, so it doesn't matter. And you're saying first I'm computing the errors is square root of mean of this thing. That's the RMS error, right? This is the expression that we've been writing up to now. And then I just say error and close the function. Now this last line is what causes the result of this calculation to be returned to the caller, right? So now if you have this, let's say we've got two vectors, x is 1 to 100, y is 3 to 102. I can compute the RMSE just by calling the function RMSE, right? If I just say RMSE xy, and this is going to be the result of the RMSE. Of course, it's going to be 2, right? Because the difference between every single element is 2, 3 and 1, 4 and 2, 5 and 3, 102 and 100. These are the two, assuming one is the actual, the other is the predicted. So if you do the RMSE, the result is going to be 2, right? So we could have used the function in all of these earlier contexts as well, right? In this case, you would have said RMSE is the function RMSE dat1, dat2. Right? In this case, you would have called the function RMSE, and the arguments you would have passed would have been dat dollar attribute 3 and dat dollar pred. Right? So you're passing two vectors, and you call the function, pass two vectors, and you can compute the RMSE that way also.